Okay, I'm gonna get started. I'm recording this session too. Get it on YouTube a little bit later in the afternoon. What I want to talk about today are some transitions in Chapter 6. A little bit on 6.1, but really focus in on 6.2. And give me a second here. I'll make sure I'm pinning my own video. I have just as a warm up here some functions in the left-hand column and some derivatives in the right-hand column. And what I'm going to do, or what I would challenge you to do, and I'll give you a little while just to think about this, is to match the functions to their derivatives. And really, what this is leading to in Chapter 6 is antiderivatives, right? We're already pretty good at taking functions in the left-hand column and taking their derivatives. It will be in the right-hand column. Really, what we have to think about for this chapter and for the next one is how to go from this column and imagine where they came from, like what function was their antiderivative. So hopefully you had a chance to look at this for a minute. If not, if you're watching the video, you can pause it and then move forward here. All right, so I'm gonna start in the left-hand corner and connect them over here to the right. So x squared plus 2, that's an easy derivative. The derivative is 2x. And ln x, that's from Chapter 5, derivative of natural log function is 1 over x. And x squared plus 10, the derivative is also 2x. And e to the 2x, we'd have to use chain rule on that, so we'd get e to the 2x times the derivative of 2x, which is 2, and I see that all the way up here. Okay, so those purple lines going from left to right, that represents differentiation. Right, so I'll just make a note of that. Right, so this is differentiation, say diff. And now some reverse mappings, just to make sure this is clear. If you were given one of these functions here and asked to take an antiderivative, those would map back to the left-hand side. So for example, the antiderivative of 1 over x is natural log x. Let's see if I can grab another color here. Hold on one sec. So I could draw an antiderivative, right, back from 1 over x to ln x. And I'll actually make a little star here. Truly, the antiderivative of 1 over x is natural log of absolute value x. And that's just because we're allowed to plug in negative numbers to 1 over x, but we're not allowed to plug in a negative number to the natural log function. So that's like one small detail there. If I had 2x, if I was trying to find the antiderivative of 2x, this is interesting because we actually see that 2x has more than one antiderivative, right? And in fact, any function has more than one antiderivative. They actually have infinitely many antiderivatives, and I'll talk briefly about how we capture all those. So the antiderivative of 2x, well, x squared plus 10 is one antiderivative of 2x, and x squared plus 2 is another antiderivative of 2x. And if we wanted to capture these in general, I think what you can see the pattern here is that any function that's x squared plus a number, if we took its derivative, we'd get 2x. Right, so that captures an entire family of functions that are all antiderivatives of 2x. All right, so let me write a couple things now. I'm going to use the notation that you encounter in Chapter 6, and that's the indefinite integral. All right, so it looks like a big sort of S there. It's the integral of 1 over x. And then often you'll see this, you'll see dx. For now, that just means that we're taking an antiderivative with respect to x and not some other variable. So now the antiderivative of 1 over x is the natural log of absolute value of x plus c, right? So c could be any constant because what we know is if we were to differentiate the natural log of absolute value x, we get the 1 over x. If it was plus 10 or plus 100 or minus pi, all those constants would go to 0 under the process of differentiation. So when we write an antiderivative that is from an indefinite integral, we should always include that plus c. That's a big emphasis in 6.1 and 6.2. Okay, what else can we write? Well, we can write that the antiderivative of 2x with respect to x will always be a function in the form of x squared plus a constant. Right, that's what we've seen so far. All this is what we'd call basic antiderivatives. So basic antiderivatives just come from the basic derivatives that we encountered in Chapter 4 and in Chapter 5. Actually, really 3 through 5. What you won't see is any like product rule or quotient rule problems that you're supposed to somehow recognize that like low D high minus high D low all over low squared. That would be very difficult to recognize just based on the form that we see here. Okay, so for this last one, the antiderivative of 2e to the 2x, that's a little bit trickier. And in order, if we were just given this, if we were just given the problem like, okay, take the antiderivative of 2e to the 2x dx, we'd have to think about this a little bit. We might even have to guess and check. So for example, especially as we're getting going on this chapter, it would be fine to guess, hey, maybe it's like 2e to the 2x. So maybe I might say, okay, is it 2e to the 2x? I know that exponential functions contain their own derivatives. Maybe it's something like this. Well, let's say you guess something like this, and you're not sure if it's quite right. Well, here's the good news. If you're doing an antiderivative problem and you're not sure if you have it right, you can always check your answer by taking a derivative. So what happens then if we take d dx of 2e to the 2x plus c? Okay, well, the plus c goes away. And then taking the derivative of 2e to the 2x, well, e to the 2x would require a chain rule, and then we'd have 2 times 2e to the 4x, so 4e to the 2x. Okay, so that tells me that actually that's not the correct antiderivative. And the reason that's a little bit tricky is because chain rule is involved. We have to kind of imagine chain rule operating backwards in order to get the correct antiderivative. And so what we can do, and I'm going to erase most of the board here except for this one problem here. What we can do is we can look for structure in the problem. And we can use additional variables, typically u, to rewrite the problem in a way that makes it easier to find. So let's see, we're trying to take the antiderivative of 2e to the 2x dx. Okay, now the technique I'm going to show you, this is where we start to get into chapter 2, is something called u-substitution. And it might not be necessary for you for this particular problem. You might be able to see exactly where this derivative came from. But it's a tool that will help you as we get into more complicated functions where you really have to use a lot of insight and pattern recognition in order to figure out where these derivatives came from. So here's what I'm going to do. I'm going to notice up here that I don't have e to the x. I have e to something else. And when we first encountered the chain rule and when we wrote formulas for product rule and quotient rule, we sometimes used a technique where we invented a variable to represent an entire function. So what I'm going to do here is I'm going to say, let's let u, I'm going to invent the variable u, and let's let it equal 2x. Okay, so now if u equals 2x, then we can differentiate this function to say du dx, so the derivative of u with respect to x, equals 2, right? Hopefully you agree with that. And now here's a slightly new take on what this derivative means. We all know this to be the derivative of u with respect to x. This actually also represents truly a fraction. We could multiply both sides by dx to obtain the following: du equals 2 dx. Now in the unit on differentials, we did use the differential form. We saw these differentials showing up. That's probably the only other context in which we've separated these two things. But what we can do now is rewrite our integral using our new variable u to make it into an easier problem. So what I'm hoping to do here is replace all the x's and all the dx's with u's and du's. And in this particular case, we can do that without too much algebra, because I see that if we let u equal 2x, well then that e to the 2x is just e to the u. What's left over then is a 2 times dx, which is precisely du. So now, while the original problem was complicated in that we didn't have just like a straight up easy derivative that we'd seen before, when I've rewritten it in terms of u, now I've turned it into a basic antiderivative problem. We know that e to the u is the derivative of e to the u plus c. Right? If we were to take the derivative of e to the u plus c, we'd get e to the u times du, times the derivative of u. And then our last step here is to remember that that u that we created that for our own purposes. That wasn't part of the original problem. Someone else could have taken a different choice for you. Someone else could have used a different variable. So we don't want to give an answer that has this like kind of unknown variable here. So the last thing I'm going to do is rewrite my answer using x's instead of u's. And so e to the u is just e to the 2x plus c. Okay, so this is the basic technique that you're going to use in 6.2. And in this first example, I've shown it with a pretty straightforward function, one where it's not too hard to see what a good choice for u would be and what du would be as well. And really what we're trying to do is we're trying to imagine the chain rule backwards. That's what we're doing when we do this u substitution. This is one of the most challenging sections for a lot of students, I think, for two reasons. One reason is that we've just begun antiderivatives. And it's sort of like, if you remember back when you were like taking algebra and pre-algebra, you probably didn't have any problem doing problems like this, like 7 squared, you like multiply 7 by 7, you get 49. But it's actually quite a step to get to this step where you're like, okay, what's the square root of 49? You have to imagine that process backwards to do square roots. And it's significantly harder than just squaring something. You have to have previous knowledge of what those perfect squares are in order to do a problem like evaluate the square root of 49. We're at a similar point in our course. We've done a lot with derivatives, and I could throw all sorts of different functions at you and expect that you could take a derivative. Now you have to kind of keep some of those relationships in mind. Remember those derivatives, because I'm asking you to do this process backwards. We're giving you the derivative, and you're coming up with the original function. Whoops. So I will pause. Okay, so I've picked 2 questions from WebAssign 6.2. Again, the constants might vary a little bit, so like this 17 might vary and this 2 might vary, but the problems should be very similar to what you're seeing on WebAssign. The first couple problems in WebAssign, I actually really like. Maybe next time I teach this course, I'm going to add more that are like this. First couple questions, they tell you what to use for you. They give you a good choice for you. And truly the difficulty in this section is your choice in you. If you pick the right choice for you, the problem becomes very easy. If you don't pick the right choice for you, it's not going to work out. It's not the end of the world, but you might get a little bit frustrated. You might have to go back and try a different choice for you. So in problem 1, they've given us this kind of complicated looking antiderivative here, x squared times the quantity, square root of x cubed plus 17. And I want you to just imagine for a moment, if we didn't know a good choice for you, like, why is this a good choice? How do we know that this will work? Well, one thing that I would say is you've noticed in the previous chapters that when you take a derivative of a polynomial, that is powers of x, all the powers drop down by 1. So one thing that I notice in this problem is that inside the square root, we have a 3rd degree polynomial, right? X cubed and then some other stuff. And then over here we have x squared and not any other stuff, right? So if we're trying to pick a good choice for you, and maybe we're thinking x cubed plus 17 is a possibility, maybe x squared is a possibility, almost always that higher power of x is going to be the telltale sign that that's our choice for you, because the process of differentiation is going to drop that power down from 3 to 2. So what we're looking for in here is some evidence of u and some evidence of what u prime would be, so the derivative of that function u. So if you have a degree 3 polynomial and a degree 2 polynomial hiding in there, almost always the degree 3 polynomial is going to be the choice for you. Okay, so let's start this process of u substitution. And again, the video might be very, very slightly different in these first couple steps. I like to write out the following, like du dx, so the derivative of u with respect to x equals 3x squared. And then as a separate step, I now multiply both sides by dx. Some people prefer to do that all at once and just to write like du equals 3x squared dx. Either one of those is fine. Okay, so now what we're looking for in the problem, we pause here and like zoom back out for a minute. And we ask ourselves, can we rewrite this integral using these pieces? Can we get rid of all our x's and can we get rid of our dx? Well, I can see for sure that this part here is going to end up being the square root of u. So that part I know I can take care of. And then what's left over is an x squared dx. So let's see, we're trying to get that in terms of u. And one thing to notice here is that du is equal to not x squared dx, but 3x squared dx. So I almost have what I need. I have an x squared dx, and if I could somehow change that into a 3x squared dx, I'd be able to substitute for du. And I want to show you probably the easiest way to do this. If you wish you had 3x squared dx in your original problem, we can actually make it into 3x squared dx. Check this out. I want 3x squared dx. I have x squared dx. So I really wish that I could multiply by 3, but I can multiply by 3 if I also cancel that by multiplying by 1/3. Okay? So see what I'm doing here? I'm multiplying by 3 inside the integral and 1/3 outside the integral. We know that there's a constant multiple rule, so multiplying by 1/3 and multiplying by 3, those cancel out, and we end up with just the same problem that we had. But now, because it's written 3x squared dx on the inside, I can do the substitution that I need. Okay? So I call this like the hacking method. You're like, oh man, I really wish I had 3x squared dx. Well, we turned it into 3x squared dx by multiplying by 3 on the inside and 1/3 on the outside, and now it exactly matches what we need to complete the substitution. And so then what we have is 1/3, right? We still have that 1/3 outside, that's important, times the indefinite integral of the square root of u du, right? So square root of x cubed plus 17 turned directly into square root of u, and the 3x squared dx turned into du. And what you know from this course is that anytime we have a root, typically it's better to write that as a power. All right, so now u to the 1/2, in order to take the antiderivative, still have my 1/3. I'm going to increase that by 1. All right, so increase the power of u by 1, so 1/2 plus 1 is 3/2. And then I have to multiply by the reciprocal of that number, right? It's like the reciprocal of the new power. So we're going to multiply that by the reciprocal of 2/3, which is of 3/2, which is 2/3. Okay? If it's unclear why I did that, remember when we take the derivative, when we take d dx of x to the n, we end up with n x to the n minus 1. Right? So what we need to do is we need to somehow cancel that. We didn't have that n out in front, and so we multiply by the reciprocal of the new power there. And as you're starting to do these problems and you're not sure if you've done it right or if you've introduced the right power there, feel free to differentiate to check your answers at the very end. So I'm not quite done with this problem. I've now taken an antiderivative, so I do need that plus c. And finally, to complete the problem, I'm going to do 2 things. You don't need to simplify this. You can write it as 1/3 something and then times 2/3. But it's a little messy here. I think I'm going to just write it out down here. 2/3 times 1/3 is 2/9. And then u is x cubed plus 17. So x cubed plus 17 to the 3/2 power plus c. And just because this is the first problem that we've done that's a little bit more complicated than just a basic problem, I'm actually going to check my answer now. So let's take d dx of the following. d dx of 2/9 times x cubed plus 17 to the 3/2 power. Okay, well, let's see. What are we going to get? We have a chain rule problem here. So we have 2/9. That's just a constant multiple. The 3/2 is going to come out in front, so 3/2, right? That comes out in front. Our x cubed plus 17 is going to be raised to the power not of 3/2, but 3/2 minus 1, which is 1/2. And then finally, by the chain root rule, we're going to have to multiply by the derivative of the inside function, which is 3x squared. And let's see what happens when we do that. Well, our 2's cancel in our fraction. We have a 3 times 3, which is 9. 9 divided by 9 is 1. And what we end up with then is x cubed plus 17 to the 1/2 power times x squared. And that's exactly what we started with. We started with x squared times the square root of x cubed plus 17. So we have now checked our work. I don't necessarily recommend that you do this for all the WebAssign problems. When it comes time to take a quiz, and especially an exam involving antiderivatives, it is definitely worth your time to go back and check. And this is something that I saw a lot in the in-person course. I've people finishing their final exams and having an hour left of extra time, handing it in without checking their answers via differentiation, and making some really silly errors that they knew better, that they could have gotten full credit on if they'd gone back and checked. Okay, I'm going to go right on to problem 5. Problem 5 has not given us a choice for u. So problem 5, we're going to need to figure out what the best choice is for u. And again, the clue is that we're looking for a function and its derivative. hiding inside here somewhere. Oh no, my favorite purple marker is slowly dying. So again, the fact that we have something in the numerator and something in the denominator, that's not the biggest clue, but oftentimes you will see u in the denominator as opposed to the numerator. That's going to be some sort of 1 over u type problem. And the bigger clue is just to look at the degree of the polynomials that we have here. So x to the 7th minus 2, that looks like a good choice to me. So we're going to just try u equals x to the 7th minus 2. If it doesn't work, we've wasted maybe a couple minutes, and we'll try something else. So don't feel bad if that happens. Okay, so if u is x squared, x to the 7th minus 2, then du dx is 7x to the 6th. Hard to talk and write at the same time. Right? And finally, du equals 7x to the 6th dx. Okay, at this point, we zoom out and say, wait, can I rewrite this in terms of u? Now, I'll say this. The math department has decided it's kind of bad form to do this piece by piece, but it's not terrible. We kind of like, when you're showing your work here, it's nice if we can change all the x's and all the dx's over to u's, because we don't really want a problem that mixes u's and x's together. But it's okay, especially on the side if you're just doing some scratch work to sort of like test out, like, okay, well, I could make that u, right? Like that's u, so that part's taken care of. And then we have x to the 6th dx. Well, that's almost what we want. X to the 6th dx is almost du. So I could do one of two things. The way I showed the last problem, I could multiply by 7 right here and multiply by 1/7 over there. I'm going to show you the second option. I don't really think any one is better than the other, but some people prefer this. Since we have this equation du equals 7x to the 6th dx, we could divide both sides by 7 and say that 1/7 du equals x to the 6th dx. And now we're able to just do that substitution without messing with our original integral. This is probably the standard way that it's taught. It doesn't require changing the original problem at all. And so now, since we have exactly x to the 6th dx, we can replace it with 1/7 du. And so now I'm ready to rewrite this indefinite integral in terms of u. So I have, let's see, I have 1/7 du. I'm going to put the du at the end here. So 1/7 du, that substitutes for the dx and the x to the 6th, so that's taken care of. And then we have just 1 over u. So our new indefinite integral is 1/7 times 1 over u du. That 1/7 we could put out in front if we want. We'll just do that in the next step. It's a constant multiple. It can be factored out. And the antiderivative of 1 over u, well, we know that the derivative of natural log is natural log x is 1 over x. The derivative of natural log u is 1 over u du. And so our antiderivative here is going to be the natural log of the absolute value of u plus c. Okay, now the reason that I'm doing the absolute value bars here, like let's remember what u is. U is x to the 7th minus 2. And depending on what value we plug in for x, so for example, if we let x equal 1, which is totally valid for the original problem, it's a function for which x equals 1 is within the domain. If we plug in x equals 1, well, we get a problem here because 1 to the 7th minus 2 is a negative number. We can't take the natural log of a negative number. And so that's why we put the absolute value bars on here, is to make sure we don't violate the domain of the natural log function. Okay, so hopefully this makes sense. The 1/7 was constant multiple, factor that out. Antiderivative of 1 over u is natural log absolute value u. I remembered my plus c. My final step now is just to rewrite this in terms of x. So I have 1/7 times the natural log of absolute value x to the 7th minus 2 plus c. All right, so again, if we make the correct choice for u, the problem flows pretty nicely. The one kind of tricky step, and we've seen this in both of the example problems so far, is that each time we haven't had a direct substitution for du. We've either needed to do a little bit of algebra on the equation involving differentials so that we can substitute directly, or multiply and divide by the same constant multiple in order to change the problem to match the substitution factor that we have here. Okay, so having done a couple examples, what I thought I'd do is just scroll through some of the problems in WebAssign 6.2 and just talk about what might be a good choice for you. I think that's the primary frustration I've heard from students when they start doing this, is not knowing what to choose for u. So I'll take a let's take a look at number take a look at number 8. Okay, so problem 8, we have x to the 7th times e raised to the x to the 8th minus 2. So there are some clues. I've already mentioned one. If we see polynomials, that is integer powers of x, positive integer powers of x, if we can find one that's one higher degree than the other, so like here we have x to the 8th, and then we have an x to the 7th out there, that tells us that x to the 8th minus 2 might be a good choice for u. This one's interesting because if you choose u to equal x to the 8th without the minus 2, you'll still get the right answer. So it is possible to solve these problems with more than one choice for u, but typically the easiest answers all involve the sort of same base case here. All right, so yeah, if I were doing this problem 8, I would choose u to equal x to the 8th minus 2 and see where I go from there. Problem 9, find the indefinite integral. Okay, this one's interesting. We have powers of e. So we have e to the 6x plus e to the negative 5x. So 2 different problems here. If I were doing this problem, I would remember that integrals follow the same rules as derivatives in terms of sums and differences. So I can do this as 2 separate indefinite integrals. I can take the antiderivative of e to the 6x, and then I can take the antiderivative of e to the negative 5x as separate problems. In fact, it might be easier to use different u's. If we choose u to equal 6x for the first antiderivative, and u to equal negative 5x for the second antiderivative, that should probably give us the things that we need here. Okay, problem 10. Okay, and you can see with u-substitution, we can actually do some pretty complex problems here. I might actually take number 10 and see if we can do that on the whiteboard here. It's got a lot of stuff going on. So let's see, we're taking the antiderivative of natural log u. Oh, thanks WebAssign for using the variable that we usually reserve for substitution to the 6th over u du. No problem 10 here. Okay, so let's switch back here to the whiteboard. Okay, so here's problem 10. And before we jump into it, let's just imagine what some of the possibilities for, well, I guess we're going to do v substitution since u is already taken here. So v, what could v equal? Let's see, v could equal maybe ln u. V could equal ln u. V could equal 1 over u. That's a possibility as well. Could we let v equal natural log u raised to the power of 6? Right, these are all possibilities. These are things that students come up with. You definitely don't want to let v equal u, because then you're just going to rewrite the whole problem with v's instead of u's. That's not going to move you forward. Really, when you're choosing the substitution, you want to do it in a way that it simplifies the structure down to a basic antiderivative that we know how to take. And if you end up trying all 3 of these before you choose the right one, don't feel bad. I think the beginning of this section does involve some trial and error. That's pretty common experience here. But we can still be strategic in which one we think is most likely. And remember, what we're looking here is we're looking for a function and its derivative. And if we think about that construction, a function and its derivative, one thing that I know is I know that the derivative of natural log u is 1 over u. And so if I see that natural log and I see a 1 over what's inside the natural log, that suggests to me that that ln u is the original function and the 1 over u is the derivative of that function. So let's try that one. Let's let v equal ln u. And again, we don't know if this is going to work, but let's see what happens when we do that. Okay, so let's do this. So let v equal natural log u, then dv du is going to be 1 over u, right? And dv equals 1 over u times dv. And now what we're trying to do is substitute so we get rid of all the u's and all the du's in the original problem. And if we do that, our original indefinite integral can be written as follows. Well, ln u, that's just v, so we have v to the 6th power, right? That's v to the 6th power, times 1 over u du. Well, 1 over u, sorry, this should be a u here, like that. So 1 over u du, 1 over u du is exactly equal to dv. And so look how much easier and nice this antiderivative is than the one that we were given. And all it took to unlock this simple antiderivative was the right choice of substitution here. Okay? When you pick right, the problem gets easier. It turns into a basic antiderivative, or maybe a basic antiderivative that differs by some constant multiple. Okay, so that's an easy problem. We're going to have v raised up to the power of 7. So we'll multiply by 1/7 to cancel that process differentiation and add c. Right? The antiderivative of v to the 6th is 1/7 v to the 7th. And then last step, v was an invented variable. The original problem was in terms of u. So I'll write my final answer as 1/7 times the natural log of u to the 7th power plus c. And that's my final answer for problem 10. If we had tried a different choice for substitution, so for example, if we'd done let v equal 1 over u, okay, well then we'd have v, and we'd have natural log of like 1 over v. The problem would just get really complicated. If the problem doesn't get simpler via your choice of substitution, probably you've chosen the wrong substitution. Okay, so one more problem. I'm not going to fully do this one, but it's pretty challenging. I want to at least talk through some of our possibilities for doing a u-substitution, help you guys get started. This is problem 13, the very last one in Web of Science 6.2. Mine has a coefficient of 5 here. Yours probably has a different number there as it changes problem to problem. And I think what makes this challenging is there's just a lot going on here. So like we know we're going to make a u-substitution, but you know, what could it be? Could it be 1 over x? Could it be negative 1 over x? Could it be e negative 1 over x? Could it be x squared, right? All of these are possibilities. And if you were to test all of these out, I actually think 2 out of the 4 would work fine here. I think there's a couple things that might make this problem a little bit easier. And I'm gonna do a couple things here. I'm gonna rewrite the original problem without any calculus, and I think it's gonna show some of the structure that we're looking for in here. And in particular, we know that there's a relationship between powers of x that sometimes helps us to figure out what the right substitution would be to make. And I'm going to do 2 things. This dividing by x to the 2nd power. Hopefully we agree that's the same as just multiplying by x to the negative 2nd power, right? So dividing by x squared is the same as multiplying by x to the negative 2nd power. So I'm going to do that just to get rid of the division part here. And then let's see, what do we have left over? We have a 5e. Okay, now one more thing, 1 over x. 1 over x is x to the negative 1st power, right? Now let me make sure I copied this down right. We have negative 1 over, yeah, okay, good. So 1 over x is x to the negative 1st power. So this power of e could be written as e to the negative x to the negative 1st power. When I write it that way, I see a clue. I see this x to the negative 1st power and this x to the negative 2nd power, right? And remember what we did in previous cases. If we had like an x to the 7th and an x to the 6th, right? We're always picking the higher power to be our choice for u. And this problem is no different. We have 2 different powers, and we're going to pick the one that's higher. It's a little bit tricky. Negative 1 is 1 more than negative 2. So I'm thinking that this is probably a good choice for u. Either x to the negative 1st power or negative x to the negative 1st power. As it turns out, it really doesn't matter which of those 2 you use. So my advice for this problem is going to be to try 2 things. First, try rewriting as negative exponents instead of having fractions with positive exponents. And then try either u equals x to the negative 1st power, or maybe u equals negative x to the negative 1st power. And I think one of those 2 should work here. Hopefully that makes sense. And at least that makes sense why I would choose those for my first experiment, is that I've identified powers of x with one being one higher than the other. The other thing that I know is if I'm dealing with powers of e, right, so I have e to some u, e to the u, the derivative of e to the u is going to be e to the u times the derivative of u. So that's another reason why I think that having the exponent be u, then the derivative of u would come out here. We know that should involve negative second powers of x. That's how I'd start this problem. So hopefully that helps you get started. I don't want to do all the problems for you because I want you to be prepared to do these on the quiz at the end of the week. Again, keep in mind these are, I think, some of the most challenging problems, and also we're just getting started on antiderivatives. There are a lot of examples that you can find. There's some Khan Academy examples. Unfortunately, a number of the Khan Academy examples involve trigonometric functions that we're not really dealing with. So if you're looking for more examples, just sort of scroll through, skip the ones involving functions that we didn't study, look for ones involving e to the x, or polynomials, or natural log x. Those are the ones that are representative of what we'll be dealing with in this course.